There is an optional help video for this experiment on the website, and it covers how to do an electric field calculation when there are two charges present. So if you're having any trouble with your pre-lab, I recommend you watch that, and it will also be helpful for doing question 8 in the lab.
So in this week's experiment, we're going to be looking at a simulation that is hosted online. So the first thing you want to do is open up a web browser like Firefox and type in the URL, the web address that is listed in your lab manual. So I've already done that. So you will wind up with a screen that looks like this, but there's two things we need to change before we start doing the experiment. So over here in this green box, there is a click box that says grid. Click on that. That gives us grid lines. Also click on Show Numbers. That just means that when we put charges and electric field sensors on here, we're going to be able to look at the numbers too, so the actual field strength. Now over here, you have some bins. So one of them has positive charges, one of them has negative charges, one of them has electric field sensors. And question 1 tells you grab a positive charge and put it somewhere on one of the grid intersections on your screen. And also grab a field sensor and put it one step away to the right of that charge. Now I will warn you that question 1C in your lab manual has a diagram, and the diagram is actually incorrect. They show this sensor 2 grid steps away rather than 1 grid step away. So ignore the diagram and just do what the text says, which is to move your sensor 1 grid step to the right of the charge. Question D, they say now move that sensor to 1 grid step locations all around the charge. So you put it here to begin with, then you move it here, then you move it here, then you move it here. So 1 grid step back and forth, 1 grid step up and down. Move it to those 4 locations. And then they say, what do you notice about the electric field's magnitude and direction? So obviously direction is just the arrow. Which direction is it pointing? And the magnitude of the electric field is written right here, this first number. So 36.7 volts per meter. Now I want to pause just a moment here and discuss what electric field is, because it's kind of this nebulous non-physical quantity and sometimes people find it a little confusing. Electric field is basically the potential for force, if that makes sense. So if I stuck a charge here instead of a sensor, it would feel a force due to this other charge. And electric field gives you an idea of how much force it would feel. Now the units they list here are volts per meter. If you break these down into SI units, it's exactly the same units as newtons per coulomb, and that might be a little less confusing. So this says 36.7 volts per meter. That's the same as 36.7 newtons per coulomb. That's saying that if you put 1 coulomb here, it would feel 36.7 newtons of force due to this other charge. So as I said, electric field is the potential for force if you put a charge here instead of a sensor. Okay, now let's go on to question E. They say now move the sensor so it's 2 grid steps to the right. So we move it over here and record the field, so write down that first number. And then the next question asks, when the distance doubled, what happened, by what factor did the electric field magnitude change? Look for obvious proportionalities. So did it get twice as big, half as big, 4 times as big? How does the number here compare to the number you got when it was sitting here? And then they say confirm your prediction by moving the charge so it's 3 grid steps away. Again, by what factor does the electric field change when you move out to this distance? If you're looking for a hint to try and understand the logic behind how it's behaving, go back to your pre-lab and look at the equation that relates electric field to distance, r. So it tells you by what factor this thing should be changing when you move it to a different r, a different distance away from the charge. Question H says now move your sensor so that it's 1/2 grid step away from the charge. And again, write down the magnitude and describe how it's changing. Question I says now take your charge and move it 1 grid step over and 1 grid step up, so basically diagonally like this. And again, how does the field magnitude compare to the value you got when it was down here? And if possible, try and explain why. Question J says if you double the distance again, so go 2 grid steps over, 2 grid steps up, so diagonally over here, what happens to the field magnitude and direction? And you should be able to explain why that happens at this point. In question K, they say use your results of this activity to sketch an electric field pattern for the positive charge. draw a number of arrows to scale on the diagram. What that basically means is grab this guy and move him around all different locations, all different angles, and just draw all those arrows on your screen. So when you're done, you'll have a piece of paper with the positive charge in the middle and a whole constellation of arrows all around it. And somebody should be able to tell when they look at your diagram that the arrows get shorter the farther away from the charge you get. That should be obvious. Question 2, we're finally on question 2, says now put the positive charge back in its bin and replace it with a negative charge. So we stick this guy here now. And again, they want you to sketch the electric field pattern. So you grab your sensor and you move it to different locations all around the charge, different angles, and you draw all the arrows in. And again, it should be obvious to somebody who looks at your diagram that the farther away the charge is, the smaller the arrow gets. Now question 3 says, remove that negative charge again, put the positive one back. So we do that. And then it says add in a large number of field sensors. So that means they're going to ask you to dump a whole bunch of sensors on the page all around so you can see a bunch of arrows all at the same time. And then you're going to be adding a second positive charge 2 grid steps away from this first one. So to begin with, I'm going to put a whole bunch of sensors on here. This is going to take me a moment to set up, so I'm just going to pause the video and then come back once I've got that set up. Okay, so I'm back now, and we see the charge and all the sensors all around it. And then they say, what happens when you take a second positive charge and you put it right here? What happens to all those arrows? What happens to their angle a little bit? How do things change? So what do the sensors show us about the electric field when we have 2 charges present instead of 1? So you're comparing what you saw here to what you see here. Now question B says remove all but 1 sensor. So again, that's going to take me just a little moment to set up, so I'm just going to pause the video here and set that up for you. Okay, I'm back now. So I've still got the 2 charges on the screen and I've got 1 sensor left. And they say to begin with, start by mapping the electric field. So you know how to do this. You just move the sensor to all different locations, different angles, different distances all around, and just draw in all the arrows. So you should have a nice big constellation of arrows by the time you're done. When you're finished with that, then they have a question for you. And they say, using a vector argument, explain why the arrow indicated, sitting here, is pointing straight up. So we've got 2 charges here, and they're both located diagonally compared to the sensor. How come this arrow points straight up, not off at an angle? Like they said, this is a vector argument. So you need to think about the x and y components of the electric field at this point due to this charge, and the x and y components of the electric field at this point due to this charge. Add them up and explain why you wind up with a total magnitude of the electric field that points straight up only. So think about x and y components of the electric fields due to each of these charges individually, and then think about how they sum up. In question 4, they say, now remove one of your positive charges and replace it with a negative charge. So we'll do that. Again, you grab your sensor and you map out the electric field. So move it all around and write in all of your arrows. So all over the place, lots of arrows. Again, make sure that it's obvious that the farther away you get, the shorter the arrows get. So map out your electric field, and when you're done, you're going to put the sensor right between these 2. And again, use a vector argument to explain why the electric field is not 0. So we've got 2 charges and our sensors right between them. How come the electric fields do not sum up to 0? So again, think about the x and y components of the electric field that this charge causes at this point, and the x and y components of the electric field due to this charge at this point, and explain why, vectorially, they do not sum up to 0. Now in question 5, they say add 8 more negative charges on top of this one. So we'll have 9 times as big a charge here as we do here, and this will be negative rather than positive. So as before, this will take me just a little bit of time to set up, so I'll just pause the video and come back when I'm ready. Okay, I'm back now, and it's hard to see, but there are 9 negative charges here in total, and 1 positive charge here in total. So as usual, you grab your sensor, and you map out the electric field. So you move all around the screen, and draw in arrows all around these two positions of charge. And they ask you to comment on how this pattern differs from the one you saw in the previous question, where you only had 1 negative charge here instead of 9 of them. Now question B, they ask you to do something kind of interesting. There is one location and one location only on this grid somewhere where the electric field goes to 0. That is, this arrow disappears entirely. So they want you to go and find it. So you move all around and you find the one location where the electric field goes to 0. So this arrow disappears entirely. Once you've found it, then you should try and use a vector argument again to explain why the field is 0 in that point. Question 6 has you actually calculate it directly, where you would actually calculate the electric field due to both of these charges individually and use a vector sum to show that they go to 0. So for example, say you found that this was the point where the field goes to 0. It isn't, but say you decided that was it. You would then have to calculate, okay, find the electric field due to this charge. I'm 2 grid steps away. The total charge was negative 9 nanocoulombs. You calculate the electric field. You calculate its direction. Then you'd do the same thing for the positive charge, where you'd have obviously a different distance away from the point and a different total charge here. And you'd calculate its electric field and its angle, and then you find the x and y components of both of those, sum them up, and you would show that yes, the electric field went to 0. And as I pointed out, it doesn't actually, but there is one location on this screen where the electric field does go to 0. So you'll find it, and then you'll show with a calculation that the field goes to 0 at that one location. Questions 7, 8, and 9 are done exclusively in the lab manual, so I'm going to show you those now. In questions 7 and 8, your group is going to be assigned 1 point on the diagram, and you have to calculate the electric field's magnitude and direction at that assigned point. So you are told in the question to assume that each grid step is 1 meter. They give you the value of K, and you also know the charge, Q, so the strength of this electric charge. And then you calculate the electric field's magnitude at whatever point your group has been assigned, and also figure out what direction it points. Now question 8 is the same idea, except it's a much more complicated situation. There are 2 electric charges there, and again your group will be assigned some point on the diagram, and you have to figure out what the electric field's strength and direction is at that point. Now it's going to have to be a vector sum of 2 fields. So say for example this was your point that you had been assigned. You would have to calculate what the electric field is at that point due to this charge. So it's a certain distance away. And you'd also have to find out what the electric field at this point is due to this charge. And it's obviously a much different distance away here. So you find those 2 electric fields, but you also need to add them up vectorially. That means you'd have to find the x and y components of the charge of the field due to this charge, and also the x and y components of the field due to this charge, and do a vector addition of them to find out what the x and y component of the magnitude of the whole field is at this location. So that's a little bit tricky. And once you're done with that, you also need to get its direction. So you do a little bit of trigonometry using the x and y components of the total field at this location. So it can be quite an involved calculation. If you're having trouble with it, call your lab instructor over to help you with that. The last question in the manual is actually not worth marks, and some lab instructors don't do it. So your lab instructor may decide that you're just not, as a class, going to do this. But what it is that everybody in the class puts their calculations from the previous 2 questions onto a lycra sheet, so a big fabric sheet, with a protractor, with a ruler, with a pen, and you draw the arrows in the right direction and to the right length. And then as a group, everybody can stretch out the lycra sheet, And your lab instructor can put heavy balls onto the sheet to mimic the charges, and then you can roll a ping pong ball around to make sure that the ping pong ball actually rolls along the direction of the arrows that you drew. Like I said, not every lab instructor will do this, so your lab instructor will tell you whether or not you are, and also whether or not you are. This last question isn't actually worth marks usually.